Okay. So let's revise what we are doing. Well, we are not just interested in this C0 2 pi or minus pi to minus pi or whatever. So we can basically dealing with continuous function, but we can deal with Riemann integrable function also. So I mean that is because of this lemma which I stated last time. I hope you know the proof. I believe if f is Riemann integrable, you can easily, if you have upper sum, lower sum, and if you using lines, you can approximate upper sum is actually given by a function. If you have a partition, then upper sum is something like this: 1 by ti plus 1. Okay, ti plus 1, where mi is the smallest value, infimum in this interval of the function. Similarly, lower sum is something like this, which is the supremum in this interval. Okay? You have, something is Riemann integrable means you have upper sum, you have lower sum, and the difference between them is less than epsilon for some partition, as some partition. Given any epsilon, you have a partition such that upper sum minus lower sum is less than epsilon. So upper sum is actually given by a function whose integral is that. Lower sum is this. Now you can define a function which takes values, continuous function. The actual function f is between these two functions. It is less than this, greater than that. You can find a continuous function between them by lines. For example, if you define it in this f of xk, whatever, plus the slope of something plus x minus xk, xk plus 1 minus, I think this will work, okay, x plus minus xk, and then f of whatever, okay. You take the slope of from here to here, whatever, signing, okay. Any bounded Riemann integrable function can be approximated by continuous function given any epsilon. Given epsilon, it is just the integral. Okay? If f is there, f minus g or square, we want square, is less than epsilon. Okay? For any Riemann integrable function f, you have a continuous function g such that this holds. So because of that, this g will be actually the Riemann integrable function will be in the L2. So you can apply the whole thing, or you could have started with the Riemann integrable function itself. Okay, that will be little bit. You could have started with that also. Whatever you want this, whatever I want, you want this proposition. F is G is a limit point. F is limit point. Correct. F is limit point. L2, because L2 is just the completion of that. Yeah, Riemann integrable function or in L2. You can treat them as a function in L2 so that you can apply Fourier transform and other things. And indeed, you can apply the same way, e power minus int, you can integrate it. This is how the Fourier coefficients will be given, and the same thing, we used that to prove something last class, okay? So we will be using it again. So maybe I will state it here, the another thing. So if I am not saying that, then I don't need this. I just say that you can take Riemann integrable function in the L2, that's all. Riemann function which are not Riemann integrable is also there. There may be much more than that. That's also there. We have defined L2 as an abstract completion of whatever. See this continuous function. Okay. I am saying you can take Riemann integrable functions in that. Bounded Riemann integrable function. Bounded means it will be, there is no integrability problem. It is just that it has to be nice. Okay. So in particular, this is Riemann-Lebesgue lemma or something. This is, even though we call it proposition, this is called, those days, we proved it very easily using Hilbert space technique. If f is bounded Riemann integrable, for continuous we need, but we will use it for, we will use it for Riemann integrable function. F is bounded Riemann integrable. Then we can define f hat n. Okay. Then f hat n Mod f at n. Okay, f at n goes to 0 as mod n goes to infinity. Is clear, right? Huh? Because we proved for bounded Riemann integrable, we proved that it is in L2. Otherwise also it's in there, but we need some condition, integrability condition. We are not going through all that. Bounded means for that we can see easily. We can approximate by continuous function. So which is just using lines, we can do that. And okay. So we have this. Okay. This in particular implies this is nothing but integral of f of t, okay, e power minus int dt, right? Why is this true? Why is this true? Exactly. We have already shown that summation f at n square is less than infinity because of that. This is exactly equal to the L2 norm of that, integral 0 to 2 pi, 1 by 2 pi, mod f of t. We have proved this. Using Hilbert space technique, we have proved this. We have proved it for any L2 function. Since we are considering any Riemann integrable function as L2 function, this is true, which we have used. And because of that, since this series is connected, f at n goes to 0. Okay. So in particular, this goes to 0. That's what it means. But then e power int is cos, the real part and imaginary part should go. So this implies for any Riemann integrable function, whatever we have there, f of t cos nt dt, okay, plus, this goes to 0. Similarly, f of t sin nt dt goes to 0. Okay, as mod n goes to infinity, mod n goes to infinity. Okay, it's just going to be minus or something. It's okay. You don't need that. Because, right, real part and imaginary part goes to 0. So this is true. This lemma, I just told you, no, we have proved this because of that. We have proved it, right? Yeah, because of that. Yeah, it's because of that. It just follows from that. Yeah, right. Okay. Okay. So, I have said these things earlier, but I'm just recording it again. Okay. Okay. Our primary aim is to, so if we had from F, okay, basically F, Riemann integrable, whatever, we have a F. From this, we construct F of F hat, which is from Z to C. Okay. We have a function, we got a function. F is in L2, it can be in L1 also if you want, whatever. But what we have is we have a function F which is Riemann integrable or continuous, then we got F hat. Okay. The question is, usually our F is in C0, 0, 2 pi. Okay. This is what we are basically considering. But when we apply something, we may use it for bounded Riemann integrable. So that's why I said, okay. So from here to C, okay, then we got F hat. Then using this F hat, we consider this SNF. SNF at T equal to summation F at N e power int, N equal to minus N to N. Okay. What we do, what's happening is the following. We have a circle or whatever, we have circle or this interval 0 to pi. By integrating with respect to int, the function f of t, multiply f of t, integrating with respect to that, we get Fourier transform, which is on the integers. Okay. Now on integers, the integration is like summation. Okay. Here you are, instead of integrating, you are summing with e power int, multiplying f of f at n with e power int, and you take the sum from minus infinity to infinity. Okay. Whether you get back that function. This is like inverse Fourier transform. This is Fourier transform. Okay. This is Fourier transform. You get f hat. Then you use f hat. Using f hat, you define some other function, a function of t you get. Whether these two are same. These two are same means, this is infinity. So if you put n and n here, whether this converges to that. So that is the question. The question is, you have Fourier transform. Then you apply inverse Fourier transform, whether you get the function. That's the question. What is the Fourier transform? F of t e power minus int is Fourier transform. Okay, 0 to 2 pi, 1 by 2 pi. Okay, this is Fourier transform. F hat, this is f hat n. Okay. Now, using f hat n, which is a function on integers, you have f hat n, you multiply by e power int. Now, there you have minus int, here you have int. Now you sum it, okay, whether you get this is equal to f of t. This is the question. You get back f. Okay, you get it as an L2 function is what we have proved. Okay, you get it as an L2 function. If you take f here, then you define SNF like this. Then SNF converges to f in L2. That is integral SNF of t minus f of t whole square dt. Okay, 1 by 2 pi whatever goes to 0. We know this. But we know that point-wise convergence is not true. That's what we have proved last time. So how we proved point-wise convergence is not true? Point-wise convergence is not true for, I mean, it's not true for all f. So last class what we proved using uniform boundedness principle and all, we want to prove that there exists functions, there exists not for one function, there exists lot of functions such that f in C0, 2 pi, okay, such that if you take SNF, then give t naught, this does not converge to f of t naught. That is the example. So instead of proving this, we prove that this diverges. If some, it cannot converge. So to prove on any point t naught, okay, if you want to get a function for SNF of t naught does not converge to f of t naught, so it diverges. Okay, to prove that it is enough to consider t naught equal to 0, because if you take f t naught, if you define f t naught at t equal to f of t naught plus t, okay, then f t naught hat is equal to e power I t naught f hat n. Okay, we proved it. Just in the integral, if you just use the definition, you get this. From this, it will follow Sn f t naught at t naught is equal to Sn f at t naught plus t. You just use the definition. Use the definition. We saw this in the end of the class. Maybe I went very fast. Okay. We got this. So because of that, I mean, we want to get the example such that this happens. I mean, last class, what I'm just revising, recall it. Okay. Such that this happens. It is enough to prove it for t naught equal to 0. Then we get it for any point using this technique. Okay. Then you can just apply. I mean, by using using a different for a different point, you get it using this technique. Okay. Okay. If it happens for f, it will happen for if it happens 0 for this, it will happen for t naught for the other function. Okay. So we want to get function such that SNF want to get functions such that this goes to infinity. I mean, this diverges, goes to infinity. Okay. For that, what we did is the following. We defined operators from here, C0, 2 pi to C, such that it takes f to Sn f, I mean, or we can directly write it. Tn, this is a linear functional. It takes values in C, it's a functional. Tn of f, Tn of f is equal to Sn of f at 0. Okay, this is an operator. Okay. Then, so we already know that Sn of f is nothing but integral over dn of at t is equal to dn of t. Is it right? F of s ds, right? This is right. Okay. Okay. We had a dn like this. Okay, and I will write the formula if needed. Dn. Then we proved that norm of Tn, we proved there was a mistake. Okay, there is a small mistake. Not mistake, error. Okay. Norm Tn is equal to integral 1 by 2 pi mod Tn t dt. This is what we proved. To prove this, how we proved it. So that's what I want to show you. If you want to prove any operator, compute any operator, for simplicity from some non-linear space to C, suppose we have any operator, or if you have x to y, for example, if you have any operator, okay, you want to compute its norm. First, so you want to prove, if this is what you have guessed what is the norm, and you want to prove it. Okay, you want to prove norm t equal to some k. Okay, what you do is first prove norm of T xi is less than or equal to k times norm xi. Okay. Once you prove this, this will imply norm T is less than or equal to k. Then get a xi in X such that norm T xi equal to k and get a xi with norm xi equal to 1 or less than or equal to 1, doesn't matter. Equal to 1, usually it will be less than or equal to 1, such that this happens. Okay. So this is one way of proving, or get a sequence xi n or depending on epsilon, psi xi n, such that T xi n is less than or equal to is greater than k minus epsilon. That's right. No, I mean T n of xi n such that, sorry, T xi n converges, norm T xi n, this is what in xi n converges to k. Okay. That's what we want. So you can prove this. That's what we did. Okay. So this is what we want to prove. So we want to prove that norm Tn is equal to this. First, from that inequality, this itself at 0, if you put 0, this will become, T is 0. So this will become dn of minus s, which is same as dn of s, because it's a sign, both sign in the numerator and denominator. So dn of minus s is same as dn of s. You get this. So from this inequality, you can take the norm f infinity out. Okay. So first we proved that norm Tn of any f is less than or equal to whatever that you call this as k. Call whatever this as k. Okay. Less than or equal to this k times norm f infinity. Okay. This we proved first. Then we wanted to get a function epsilon. There was a small mistake. F epsilon was just dn by 1 plus dn square plus epsilon square. Okay. I put 1 here, it should be this. Okay. Yeah. If you write it, you will get it. If you exactly write it, you will get. Okay. That's all. As epsilon goes to 0, you will get it. The thing is, you cannot use dn by mod dn because that may become 0. So you have to take it like this. I mean, that's not continuous. So that's why you have to take it like this and you can prove it. Okay. So once you have proved it, these things prove that norm, and then we proved that that integral goes to infinity. Okay. So that will imply that norm Tn goes to infinity as n goes to infinity. Okay. But then by uniform, the reverse of uniform boundedness principle, which we need proof. The actual uniform boundedness principle which we have proved, from that you will get one function such that this happens. But if you use the proof, it's actually true that if Tn converges to 0, then there exists a set, let's say S contained in C0, 0 to pi, where S is dense G delta set. Okay. G delta set such that Tn of f, okay, goes to infinity as n goes to infinity. You wanted to ask something? What were you asking? Yeah, this is less than or equal to 1. Now, norm infinity, this norm in above what? Where? Yeah, this is a number. This is just complex number. Okay, this is f infinity. No, this is for all f. What do you mean by f infinity bounded by something? No, if you take f infinity less than 1, then this is not there. It's less than or equal to k. This norm is a supremum over all f such that norm infinity less than or equal to 1. If you prove it, okay, then it is, if f infinity is less than 1, then this is less than k. Okay. Okay. So from that we get a G delta set which happens all that. So the proof exactly the norm, exactly the definition of the norm of the operator. Yeah. Okay. Fine. Okay. So we get a large set, dense set, which is also a G delta set, where this conversion does not happen at 0. The Fourier series diverges there. Okay. That's what we have proved. So now we want to see somewhere where it actually converges. Okay. That's what we want to prove. We want to prove convergence theorem. We have proved a divergence fact or whatever, divergence example. It's not even example. You can call it divergence theorem. because it gives a large number of it and it doesn't specify it. Okay, so oh no, sorry. Yeah, my fingerprint doesn't work. This I want to put it in silent mode. Mm. Okay. So we want to prove something. So for that, let's see an example. There are many examples where you can actually compute, of course, Fourier series is Fourier coefficient, whatever the f hat n is just an integral you have to compute. Okay, and it's integrating with respect to cos in theta, sin in theta. You can compute and you can compute. You can really compute the Fourier transform Fourier series for many functions. Okay, so that is just a high school mathematics, +2 mathematics. Okay, so we will prove general. We will see general facts. So suppose let f is in C0, 0 to pi, okay, and suppose integral 0 to 2 pi f is equal to 0. There are many such functions like that. Then define f of t integral 0 to t f of s ds. Okay, you can define a function like that. Because of this condition, f is in on the end points, the value coincides for f of t because of this condition. Okay, because the integral 0 to 2 pi is 0. So because of that, f of 0 is equal to f of 2 pi. So this is in this class. Okay. Now you can calculate f hat at n. F hat at n is equal to 1 by 2 pi, integral 0 to 2 pi, integral 0 to t, f of s ds e power minus int dt. You just use integration by parts, and whatever you get in the first term, it will be 0 because the nth term they coincide, both the functions f. Okay, this if you differentiate, you get f, of course. So you get only this term, integral 0 to 2 pi, 1 by 2 pi, f of s e power minus int by in. This is what you get. Here, 0 to t, 0 to 2 pi. Okay. Now this is just f hat n by minus in. This is minus in. Okay. This is what it says. Huh? Integration by parts. Huh? What is mechanical, electrical about it? Huh? Integration by parts, there is only one integration by part. Huh? Integration by parts. You just first differentiate this and then integrate it. That's what you do. Integration by parts is a rigorous formula. You get it from product formula of the. Huh? Of course, if you integrate first integration by parts, you will have something you have to evaluate between endpoints. I said that, and I mean you write it. It's an exercise. The endpoints is 0; they coincide, so that term will not be there. Only the other way, the UV, that whatever you evaluate, that will not be there. Only this will be there. If you differentiate this, you get f. If you integrate it, you get this. That's all. Okay. So this is just integration by parts. Okay. Okay. So we want to use this example 1. If where okay, there we have you want to take ST, that's okay. There is no T. Okay, doesn't yeah, I have confused it with yeah, this is what you are no, the T is here, no, so that's why I used S. This T is here, no, that's why I use S. So there we have got S only. Okay, we have S. The T is somewhere there. Okay. So if F is differentiable, F is continuously differentiable, See, well, we can identify, I mean, you may be worried about the differentiability at the endpoints, 0 or 2 pi, but you can consider as a function defined on whole of R, okay, as a periodic function. Then the f prime makes sense in the endpoint also. Okay, so we consider that way, or you can look at the circle. There is no problem about circle. Okay, so f is in, so that's what we mean. F is in C1. Okay, the corresponding C1. That I'm not mentioning purposely. I'm not mentioning that f is differentiable and the derivative is also continuous. Okay, then f at n equal to yeah 1 by in f prime at n, right? Right. From this formula, this is direct, right? If you integrate f hat, you will get, if you integrate f prime, you will get f by that formula, fundamental theorem of calculus. Okay. This is differentiable and continuous. I mean, differentiable and the derivative is continuous. That's what it means. F is C1. Then f is given, f is equal to integral of f prime. So I am just using that. Okay. This is more general. This is little bit restrictive. Yeah. Exactly. Exactly. That's why I said you consider it as a periodic function. So the f prime will also be periodic, right? So that's why. So you don't have any confusion. Okay. Or if it is a function in circle, it will be a derivative also in the circle. Okay. So that's what we take. So only the problem may be in the endpoint. So, but if you consider this way, there is no problem about it. So you have a part like this. Okay. There is no differentiability of Fourier transform. The function is differentiable. What is the extra condition? Differentiable is the extra condition. What is the extra condition? A function is differentiable. That is an extra condition on the function, and it is continuous. What else? What is the input unit step? If f is in C1, I am saying f hat n is equal to this. This is something which connects the Fourier series of f hat, f prime and f. Okay, f is in C1, then the Fourier transform of f hat is 1 by in f hat f prime hat of n. Okay, that's what I have written. Okay. So example 3, if f is twice differentiable, okay, then f hat n is equal to 1 by, you have in, you have another in, so this will become 1 by minus n square f double prime hat n, right? I have just applied it again. Okay, that's all. Now we get a proposition. If f is twice differentiable, continuous and twice differentiable, that's what I mean by C2. I'm not writing there. Then SNF converges uniformly. Okay. You get it very easily. Of course, the proof is mod of f hat n, okay, is equal to 1 by minus, it will go away, 1 by n square times mod of f triple hat n. Okay. Notice for any function, this is for any function. Notice for any, I have said it earlier, I'm saying it again. F hat n is equal to integral 0 to 2 pi. This is for any function, okay? F of t e power minus in t dt, whatever. Okay. Mod of this is less than or equal to, you take the mod of here, this will go away. Okay, this is just a number, the L1 norm of this. Okay. This is true for any f. Okay. So in particular, this will be less than or equal to 1 by n square. The L2 norm, of course, f prime is a continuous and it's bounded and all that. So L2 norm of f prime, sorry, L1 norm of f prime. There is no n here, right? So this implies summation mod f hat n is less than infinity. Okay, minus n to minus infinity to infinity. Okay, there is no t or anything involved. Okay, t means e power int. So this implies summation minus infinity to infinity f at n e power int. Okay, converges uniformly for all. Converges uniformly. That's all. If you take the mod of that, that's what you get, and this is true. Here, f at n is this inequality. You have e power int, I take the mod, it goes away. F at n is equal to f of t e power minus int. You take the mod, this is less than or equal to mod of this, which is less than or equal to, you can take the mod inside in an integral. E power int mod is 1, it goes away. That's all. Okay?
The quantum convergence need not be f of
t. Exactly. It will be f of t, we will come to that. Here I am only saying it converges uniformly. It cannot converge to anything else. It has to converge to f of t. We will make sure later. Okay. This just says that it converges uniformly. So if this Sn of whatever Sn of converges uniformly, if f is twice differentiable. Actually, it is enough if it is once differentiable. This is easy, so that's why I went through that proof. It is actually true if it is once differentiable also. Proposition. If f is in C1, okay, then SNF converges uniformly. We will prove possibly in the next class, not in this class, something called Fedger's theorem. Okay, that will prove that this limit has to be f of t. Okay, we will prove later. Today we are only proving, we are basically observing that it is convergent. Okay, the limit will be equal to that. Okay, proof. If it is once differentiable, f at n is equal to 1 by in f prime at n, right? Yeah, right? We have got this. Okay. Now SNF, whatever, SNF, let's not write FNF, summation minus n to n, okay, f at n, e power int. You want to take mod of that, so we want to only prove this. We want to take this. We want to consider this only, right? This is equal to summation 1 by n, okay, mod of f at f prime at n. Can anyone give me an idea how to prove this? We want to prove this is less than infinity. I mean, this goes to, I will of course give you immediately marks if you tell me. I shouldn't have seen it before. Huh? You want to prove that this is convergent. Half of what? Then what will happen? You have 1 by n here, which is not convergent. Okay, you had f at n. That's what you want to prove it convergent. Okay, but what do you have?
no mod f of n minus
Mod f of n minus. How is it going to help you?
di by I converges.
Sigma?
It's like it, I'm just giving it correctly. Sigma di by I converges.
What is a?
Real number.
Okay.
That implies that sigma even plus up to a by n goes to 0.
Okay. So
That's what it implies. So I say that here we have sigma a.
you are saying sigma a n by n. Huh? What theorem? What does it say? F1 is converging to F1. Where? F1 is converging to F dash and where? Okay. We don't have anything yet. We had twice differentiable and proved that. We don't have, we have only once differentiability. This one differentiable once. Okay. And we have this. None of this is convergent. This is not convergent, but the product is convergent. That's what I want to prove. Okay. No, I want to prove, sorry, I want to prove uniform convergence. I basically want to prove that now one second, let me make the correct statement, and then if I put mod, you will get this. That's also okay. No, that's also okay. There's no problem. I could have taken something else also. Okay. You want to, the same thing we want to prove. This is, if you take minus infinity to infinity, is less than infinity. That's what it means by the for SNF is uniformly convergent. SNF is with infinity, infinity here, mod of this. I mean, this is absolutely convergent for SNF. Okay. So why is this convergent? Correct. Correct. So, correct. Very good. What's your name? Huh? Okay. I'll give you some marks for that. It is Cauchy-Schwarz. It is just Cauchy-Schwarz. Okay. So this is, we have 1 by n square is convergent. We have this is convergent, and from that you will get it. So this is equal to summation minus n to n 1 by n square whole power half. This is less than or equal to, and summation f hat n square whole power half. Okay. This is convergent because this is just equal to norm f2, and this is of course convergent. So this is less than, just Cauchy-Schwarz. Okay. This is Cauchy-Schwarz. That's all. Okay. Now we will prove little bit more difficult theorem. So if it is once differentiable, that is enough, it is convergent. Twice differentiable, also convergent, of course. I have time. So Fourier series is nice most of the time. Okay. And of course, we have to prove the limit is that, that will be proven in the next class. Okay. Okay. So this is little bit slightly involved theorem. Let f be. So here for convenience, I take minus pi to pi. You will see why I am taking it. Okay. From the proof. This is okay. You can just shift the function. But if you shift the function, there is one thing. We have shown that e power int, phi nt equal to e power int is an orthogonal basis. But if you shift it, you have to add pi. So this will become minus int. Right? If you add a pi, it will become minus int. Sign will change to sign. But that doesn't matter because minus n, both this is n varies in z. Okay. So this is okay. You will get the same orthonormal basis except, yeah, exactly minus n. So it's okay. You can use the same definition. And whatever the dn, whatever we have got, that is just summing over e power int between minus n to n. So that's also symmetric. So there is no difference. Okay. Except that minus n has become n has become minus n. Okay. So we can freely using. There is no difference. Okay. So I don't have to go through define all those things again. Okay. Okay. So I mean, you can actually define for any interval and work with that. Okay. Then you have to do the scaling and you have to do many things. Okay. Any interval you can identify with circle, functions in circle, provided it coincides in the function coincides in the endpoints. Okay. Okay. Now you have something like this, and suppose there exists a t naught in this, such that integral minus pi to pi f of t minus f of t naught divided by t minus t naught mod dt. This is what is called integrability condition. This is less than infinity. You can see that that t naught is somewhere in between this, so there it can blow up. Okay. So this is less than infinity. Okay. Then S and F, this is point-wise convergence. I am giving you point-wise convergence. T naught converges to f of t naught. Okay. Statement is clear. Okay. So example where this condition is satisfied. Okay. If something called Lipschitz continuous or something, there it's satisfied. Or if you take f of t minus f of t naught minus f of t naught is less than or equal to some k times t minus t naught power alpha. Alpha, any alpha greater than 0, it will work, I think. Right? If you take alpha greater than 0, alpha is greater than 1. Eh? If it is greater than 1, what will happen? Then it will become t, if you take t minus alpha, you will get t minus t alpha power some alpha minus 1, which is positive. That's integrable, no? X power alpha is integrable in the any interval, any finite interval. It's a continuous function. So alpha greater than 1 is fine. Alpha equal to 1, then it is just f of t minus f of t naught, t minus t naught is less than k. Any constant function is integrable. Okay. So if it is less than 1, if alpha is less than 1 greater than 0, then f of t minus f of t naught mod t minus t naught is less than or equal to k times t minus t naught alpha minus 1. This is negative. But till it doesn't go, it doesn't touch minus 1. Okay. If you integrate it, if it is minus 1, you will get log term. If it is before that, you will get a 1 will be added. If you integrate, 1 will be added, and you will get a number. What I am saying is, in your exercise, integral x alpha, alpha greater than minus 1, okay, is integrable. Alpha equal to minus 1, you will get log. Okay, that is not integrable. That can become 0. I mean, where it blows up. See, you have t minus t naught. T minus t naught means what? Near t naught it blows up. X alpha blows up near 0. Okay. So if your alpha is equal to minus 1, this will be infinity. If it is strictly greater than 1, this will work. So okay. So for all these things, for all this alpha greater than 0, okay, that condition is satisfied. This is an example. In particular, if it is Lipschitz continuous or something, this is true. Okay, okay, proof. So we want to prove Sn ft naught equal to ft naught. Okay. So by replacing, I mean, without loss of generality, we can assume t0 equal to 0. Okay. Because you can, I mean, since we have already seen this, Sn ft naught is equal to Sn f t naught. Okay, if you want. T naught is a translation by T naught. We have already seen that, right? So because of that, without loss of generality, we have already said this. So without loss of generality, assume T naught equal to 0. Okay. Otherwise, you replace it by a different function for which that will convergence will happen at 0, and then you can bring it to T naught. Okay. So it's enough to consider T naught equal to 0. Okay. Now let's go one by one. So what do you want to consider? We want to consider f of at 0. I mean, t naught equal to 0. So at t naught, this is true. So let's write the condition. The condition we have is, of course, t naught equal to 0. That's all. Okay, that's what we have. The condition. Okay. So we want to consider Sn of f at 0 minus f of 0. This goes to 0. This goes to 0 as n goes to infinity. That's what we want to prove. We want to consider this term. Okay. Maybe mod of this. This is equal to, we know, equal to the dnt. That's what dnt. And here the t is 0. Okay. So we have sine f of t sine n plus half t by sine t by 2. Okay. Or I will just write dnt. We will come back to this. Okay. dnt f of t dt. So I think we have already noticed we have already, I mean, this is true. It depends on d and t is 1 by 2 pi, I think, whatever, equals 1. D and t is nothing but summation minus ntn e power int, right? That's what d and t is. But e power int, when n not equal to 0, the integral vanish between 0 to 2 pi. Only at 1. At 1, the integral is 2 pi. So 1 by 2 pi is 1. Okay, so this is true. Okay. So this implies we can write it as integral 1 by 2 pi d and t just f of 0 dt. You can write it like this. F of 0. Yeah, I have written f of 0. You are not able to see. Okay. Okay. So what will let me now introduce the sign and other things. So this is, we want to show this is 0. So that is less than or equal to, it's okay. I'll take the thing outside, 1 by 2 pi mod outside itself. Okay. So sine n plus half t divided by sine t by 2. Okay. Then I have, okay, I take the mod inside. Mod of this. I hope that's okay. Minus pi to pi. Minus pi to pi. Sorry, this is minus pi to pi. I mean, if I write the integral 0 to 2 pi, please remember it's minus pi to pi. Sine n plus half, correct. Sine n plus half t. Okay. I mean, it's not n plus half t, it's n plus half t. Okay. Then you have mod of f of t minus f of 0. Okay. dt. Okay. We have to show this goes to 0. Okay. I split the integral between some delta for delta greater than 0. I split the integral between delta to minus delta. So this is where I like the minus pi to pi, the integral. Okay, so you can write it. Otherwise, it will be complicated. If you take some t naught and t naught plus delta, t naught minus delta, it will be messy. So I consider near 0. Okay, so that's why minus delta to delta. So then you have, and this is sine, this is less than 1. You can swallow it. Okay, so this is sine t by 2. Okay, and what we have is f of t minus f of 0 dt. That's all we have, the first term. And here, I hope you are convenient with this notation. This is just the integration between pi to minus pi to minus delta, delta to pi. It is just the integration in the complement. Okay. Okay. So then this is okay. So f of t minus f naught divided by sine t by 2. Okay, sine n plus half. I hope this is okay. Okay. Okay, now we will show this term first goes to 0 and this term goes to 0. And first we will handle this term and then we will handle this term. Not that we will not show this term goes to 0, we will handle it somehow. Okay, by taking lim sup or something, we will handle it. Okay. Okay, so we want to show this goes to 0. Okay, notice that when t is, this is in the complement of minus delta delta, so 0 is not there. So this is not going to vanish. This may vanish, but this is not going to vanish. So this is a nice function. This is a continuous function. Okay. Now you take g of t equal to whatever mod f of t minus f naught by sine t by 2, whatever. Okay. If t is in minus delta to delta complement. Okay, and equal to 0 if t is in minus delta delta minus delta delta. A new function g of t. Okay, then g is bounded Riemann integrable. It is except 2 points, it's continuous everywhere. Okay, so g is Riemann integrable. Okay, then we have g hat n goes to 0 as n goes to mod n goes to infinity. Okay, okay. So this implies we may have more terms. Oh, I said g of t. Okay, I need to have consider two functions g1t, g2t. Let's come to that. Well, I will directly say this. We may not need this. I mean, we made something similar. Let it be, but I will change the function. That's all. I will use similar function. This thing is equal to the second term. Okay, let me call this as a delta n. This term. Okay, and this I call it as b delta n. Okay. If you have written, it's okay. There is no. I'm going to change it. That's all. Okay. Now b delta n, whatever we have, okay, is equal to, I expand the sin n plus half t. Sin a plus b is sin a cos b cos a sin b, right? So b delta n is equal to integral the over minus delta delta complement. Okay, f of t minus f naught. These things are nice function. Sin t by 2. Then cos nt sin nt, so cos nt, and then sin half t will cancel with this. So we don't have, I mean, we have mod, so cos that can cancel with this. And from here minus delta to delta, okay, f of t minus f naught. Okay, then here we have sin nt cos t by 2 sin t by 2. But then when 0 is not there in the interval, cos t by 2 by sin t by 2 is, sin t by 2 is not going to vanish. It's still a continuous function. So you have a nice function here. Okay, and you can define it to be 0 as it is. Okay, shall I write it as g delta is this? Okay, if you if you have a function, let me write it here. Sorry, I change it like this. Okay, if one second, let me write. If g is a function on minus delta delta complement, okay, then you define g tilde, okay, equal to g of t if t is in that complement, and equal to 0 if t is in minus delta delta. Okay, delta complement. Here also complement. Sin and cos and t sin t by 2. That sin t by 2 will cancel with the denominator. Second term sin into cos t by 2 by sin t by 2. Sin nt by cos t by 2 sin t by 2. I am just cos a plus b formula. Okay. And you take this as g1, this as g2. This is just the Fourier coefficient, cos coefficient, trigonometric coefficient or something. So these two terms goes to 0, as n goes to infinity, right? If you take any Riemann integrable function, f hat n goes to 0. Okay, that means the integral of that function with cos nt goes to 0, sin nt goes to 0. That's what it's so. So these two terms goes to 0. Okay, so b delta n goes to 0. So b delta n goes to 0 as n goes to infinity. Okay, we have to worry about a delta n only. Okay, now we consider a delta n, that is equal to minus delta to delta f of t minus f naught divided by sin t by 2. Okay, that's what we have, dt, right? That's what we have. Where did I write? Yeah. Okay, that's what we have. This is, of course, less than or equal to this function t by sin t is a nice function when you don't include the pi and minus pi. Okay, it's a nice function. When you sin t is going to wait a minute, what? Yeah, I mean, at 0 it's going to be 1. Limit is 1. You can define it to be 1. Okay, so this is a nice function near 0. So you can take a slightly longer interval. So this is, let m is equal to supremum of this t by sin p. Okay, t is in minus pi by 2 to pi by 2 if you want. Okay, that's enough for us because we are going to take between delta and this. Okay, so the a delta n is less than or equal to some m times integral minus delta to delta f of t minus f naught divided by so t by 2. So the 2 also I am taking it inside. Okay. Okay. Maybe there is a 1 by 2 pi somewhere. I have fallen it everything inside m. Okay. Maybe something. Okay. So this is what we have. Okay. Now this is integrable. Okay. This is integrable. This is integrable is the condition. If it is integrable, then you should know that as delta goes to 0, this goes to 0. Okay, that's what we will use now. Okay. Now we started with something. Lim sup of Sn f 0. Okay, that's okay. Okay, maybe mod of this. Okay, mod of this. Okay, lim sup. We have to prove lim sup is 0. Okay, to prove something is 0. Lim sup is less than or equal to the other term. You are taking lim sup. Other term limit is 0, so it will go to 0. Okay, so you don't care. So you only care about this. So this is just lim sup over n of this minus delta to delta some integrable function f of t minus f naught divided by t minus 0 dt. Okay, that's what we have. There is no n here. There is no n here. So you can take limit delta going to 0. You can take, this is true for all delta. You can take limit delta going to 0. So this equal to 0. Yeah, say
Around 0,0.
around.
This is continuous.
Exactly. Exactly. Now, any integrable function is enough. Any integrable function, delta to delta, if you approach a point, integral 0 to t as d going to 0, that will be 0, right? It's maybe not. Maybe where are we using it? No, no. Integral 0 to t f of t dt. That function is continuous. That's what we are using.
That is continuous.
Which is you are using the continuity of f. Right. That's what I'm saying. Yeah, correct. That's precisely we are using. Same thing. For any integrable function, there, that's what you are using. Correct. Okay. So because of the discipline. Here, this is equal to this is something. Here, this SNF has two terms, A delta, B delta. B delta lim sup, if you take that goes to 0. So only A delta you have to worry. So I have got A delta. And I have swallowed n. There is no n here. And this is an integrable function. So this is true for all delta. So you can take delta go to 0. Delta go to 0, this goes to 0. That's all. You take delta go to 0. This is true for all delta. Okay. And for all delta, that is the other thing is going to 0. Okay. You have taken it already 0. This is lim sup is less than or equal to 0. So that's why I have written the statement. That's why I don't want to take before lim sup. I took the lim sup so that the other term is not there at all. This is true for all delta. Now you take limit delta going to 0, that this will, you get this. So we are done. I have finished before time. I want to give exercise, but I don't precisely remember the condition. Okay, I will give it in the beginning of next class. Okay, any doubt? Theorem. This theorem doesn't have a name as far as I know. There is something called Dirichlet's theorem, Feder's theorem. This is not, but usually the theorem is if it is Lipschitz continuous, then Fourier thing converges. Okay. You can look at notes of Thangavelu, Kesavan, or whatever, somewhere. Thangavelu, Kesavan. Some English name also, but I don't remember exactly the spelling. Quarner or something. There are, okay. Folland, you can look at the book, but that will have too many things. So you have to, it will be difficult. But this is fairly clear, I believe. I'll do next time.